Welcome. I've been expecting you. Well, since it's that time of the year, Halloween is just around the corner, I decided to do a circuit with a bit of a holiday theme. And what I want to talk to you about today is this thing. This circuit is also known as a theremin. A circuit that can create some weird noises and has been used in the past for generating music, spooky soundtracks, and lots of other things. So if you're curious about how this thing is built, how it works, and how you can build your own, of course, then keep watching. So let's start with a short history lesson. This thing is called a theremin, but it's also known under various other names, either an Etraphone or Theremin phone or Theremin Vox or whatever. There were multiple names associated with this thing. And this was created back in the 1920s and then patented in 1928 by its creator, Leon Theremin. Now this thing was created in an age when radio was just becoming popular, TV was still an experimental device, and then this guy comes along and creates a device that you can play without touching. Now, even today, something that works on this principle is quite impressive, but back then, it must have seemed witchcraft. And the most amazing part about it, at least in my opinion, is the sheer simplicity of the circuit behind this. Now, you can build this thing in its simplest form with around 4 transistors and 2 diodes. Now, the one that I've built has a few more components, but that's not really the point. So, how does it work? Well, you may have noticed by the sound that it produces that it can produce a single frequency sound that has a variable volume. And this is exactly what we can see in this block diagram. The circuit has a part that generates a signal to control the volume, and the circuit has a part that generates the audio frequency that we can actually hear. And then you need to combine the two. So let's see how we can do this. Let's start with how we can generate the variable frequency sound. Now, to explain this, we need to understand what heterodyning is. Basically, it's a signal processing technique in which you can take 2 signal sources. In this case, I've got a sine wave at 300 kHz and then a sine wave at 302 kHz, both having the same amplitude, and you need to combine them. And the easiest way to perform this is by this sort of simple circuitry, in which the AC part of both signals is combined using some capacitors into a single node, which is pulled to ground by a resistor. So what are we expecting to happen? Well, if we look at the 2 signals, we can see that since they are of different frequency, they have different wavelengths, and although they start off almost perfectly in phase, at some point they end up being completely out of phase. So by doing this sort of circuit, you will end up adding up the 2 signals. When they are in phase, the sum will be double of the initial signal. When they are out of phase, the sum will be nothing. And we get something that looks like this. We can clearly see how the 2 signals are being added up together. So by heterodyning, you can obtain sums of frequencies and differences of frequencies. In this case, what we're getting and what we're interested in is the difference in the 2 frequencies. Now, if we measure this difference, we can see that we have almost exactly 2 kHz, which is the difference between 300 and 302 kHz, the initial 2 sounds. Now, at this point, we still have roughly 300 kHz signals. So this red thing is still a very high frequency signal. So what do we do with this? How can we extract something usable from this? Well, we need a circuit like this. So we take the 2 signals, we combine them, and then we perform a simple detection. Basically what you would do in a normal AM radio. What you're interested in is this envelope. So what is the maximum out of this frequency combination? And what we get looks something like this. So it's not perfectly clean, there's still some remnants of the initial high frequency, but this time we get an audio signal. So a signal that is in the audio spectrum. So how do we generate the initial signals? Well, for that we need something like this. This is an electronic oscillator, also known as the Colpitts type of oscillator. And basically what this does, after it starts up of course, is create our high frequency signal, at least one of them. Now the frequency here, so this is running at around 370 kilohertz. The frequency is generated by the resonant oscillator, so the coil and the capacitors. Now to vary the frequency of this oscillator, we need to act either on the inductance or on the capacitance. So let's see how we can do this. So to explain how we can get a variable frequency oscillator, I set up this little experiment. So what I got here is a capacitance meter connected to a piece of metal. Now watch what happens with the value when I bring my hand closer. So I'm not touching it, I'm just going ever so slightly closer. And you can see that the capacitance that the meter is measuring is increasing. Now, not by a lot, roughly a picofarad, but it's something. Now we can make this work even better if the other terminal of the meter is grounded, so connected to me. In this case our initial capacity is already much bigger, around 3 picofarads, but that can be adjusted of course. And now if I bring my hand closer, we get a much bigger capacity being measured. Basically what's going on is that I'm building a capacitor in which one terminal is this piece of metal and the other terminal is my hand. And basically this is what we need to build a theremin. We need a hand, so the player's hand, and a piece of metal that will act as an antenna. And the electronic device will react to the capacitance generated by the proximity of the antenna to the hand. So the full circuit needed to generate the variable audio sound will look something like this. You need two oscillators, one of which has an antenna that has variable capacitance based on the proximity of the player. You need to combine the two signals to obtain the heterodyne signal, and then you need to detect it to finally obtain the audio signal. Let's see this thing in action. So we have the two high frequency signals running at very high frequency but whose frequency is different nevertheless. We have the combined signal whose envelope frequency varies based on the difference of the two initial signals. And finally we have this cyan-ish color, which is the audio signal. And this on its own is in the audio spectrum. Now based on the capacity of the antenna, its frequency will vary, because the difference between the reference oscillator and the variable oscillator will vary. And these are the first two transistors and diode needed for this circuit. Now one thing to keep in mind is that since your antenna will have a very small capacitance, the way to obtain a very large variation in output frequency is to use huge inductors. So right now I'm simulating with a 1 millihenry inductor, but you can work with higher values than this. The important thing is to make sure that your extra 1 or 2 picofarads of antenna capacitance will be able to vary your oscillator frequency enough to get a usable response. Now let's move on to the volume part. So before talking about how we can generate the signal coming from the volume circuitry, we need to talk about what we're going to do with this signal. So what I got here is an audio frequency sine wave, so this would be coming from our pitch oscillator circuitry. And I also have a pulse going from 0.4 to 0.8 volts, which would be the response coming from the volume circuitry. Now to combine the two, you need a bit of circuitry which is known as a VCA, or a voltage controlled amplifier. Now, there are simpler ways of doing this. In its most basic form, it will contain a single transistor, but from what I could figure out, that circuit will end up distorting the signal. This is a more complicated version of this circuit, in which I have a comparator and a transistor that regulates the current going through the comparator. So by using this circuit, I take my original audio sound, I take the voltage ramp, and by combining these two, I get this sort of response. So my output's amplitude will vary based on the voltage injected into this lower part of the circuit. So by controlling the current going through the two arms of the comparator, I can vary the amplitude of the output signal. And the good thing about it is that there's minimal distortion. So even when the signal is with a very low amplitude, there is some distortion, but it's quite small. And afterwards, the signal is almost unaffected. Only its amplitude is varied. Now, of course, there are better ways of doing this circuit, much more complicated ways, but this circuit is good enough. So now let's see where we get this volume control signal. Basically, we need again an oscillator whose frequency will be variable. So in this case, I'm simulating a variable frequency AC signal, and then we need a filter. So here I'm injecting my AC signal through this capacitor through C1 into my filter L1C3, and then detecting the output. So if we run this, we can see that our filter has a resonance point in which the amplitude of the signal on it will be maximum, and then after detection we get our output signal, which again has this maximum amplitude. But this time we're talking about a DC signal, and this is what is going to be used to drive our voltage controlled amplifier. So as long as the frequency of the oscillator is very close to this resonance point, any small variation in its frequency will have a large variation on the output voltage. And this you can use to vary the volume of the final sound. So let's see how this entire thing would look like put together. Well, I came up with something that looks like this. It contains most of the previous circuitry with some minor modifications. So let's go through them one by one. So first of all, here are my oscillators for generating the sound, so the pitch signal. And what's different about these is the transistors. I went from NPNs to PNP type of transistors so that my oscillator, so the LC circuit, is connected to ground. This way the capacity that the antenna brings to the circuit is actually connected in parallel with the circuit. It's no longer connected to a different supply rail other than where the oscillator is. Secondly, I added these resistors in series with the capacitors. This way the load that the oscillator sees is reduced, so it sees a much larger impedance. Same sort of circuit is used when I'm taking the audio signal from the detection circuit into the VCA. Also, I switched the direction in which the diode is pointing, and there's very good reason for this. So if we look at the signal that the oscillator is producing, half of it is straight, half of it is sine wavy. And this time, since I'm using a PNP type of oscillator, the negative half is sine wavy, the positive half is straight. So by switching the direction of the diode, I'm cutting off the straight edge and being left with the sine wavy part. This way the part of the signal that I'm going to use actually looks almost like a sine wave. So it doesn't look all messed up like the positive half. On the volume control circuit side, again I switched the oscillator to a PNP type, and other than that, not much has changed. And basically these are all the components needed to build a Theremin. You have the 3 transistors needed for the oscillators, the 2 diodes needed to rectify the high frequency signal, and then a voltage controlled amplifier, which can be built with anything from 1 transistor up to integrated circuits and op amps and so on. So let's see how this thing looks like in action. So being such a huge circuitry, it's working extremely slowly. We can see how the 2 signals coming from the 2 oscillators combine. So this is the heterodyning in action. Then when we look at the detected signal, we can barely see anything. If we look on the volume control side, we can see that there is some current coming through this. Again, it's not perfectly straight, it's not perfectly filtered. This circuit still needs a bit of work, so the circuit is not finished, but it's operational. And finally, if we look at the output signal, we can't see a thing. So right now, the circuitry is still stabilizing, which is taking a while. I mean, at the speed at which the simulator is going, it will take, I don't know, half an hour until everything reaches a stable point. But we can look at the circuit in a much better way if we actually build it. It's been so long since I worked with through-hole components. Ever since I started working in a company that lives in the 21st century, I was reduced to surface mount components. I mean, don't get me wrong. After you get used to working with those, you quickly see the advantages. You can make smaller and more compact circuits, and they're also easier to assemble in mass production. But for this thing, the Theremin, small and compact is not really a good thing. I mean, you need physical distance between components, since you're working with tiny variations in capacity, which are below 1 picofarad. The whole circuit I'm building could fit in a matchbox, but then it just wouldn't work. So for this particular application, through-hole components are more useful. So this is the assembled circuit, and let's go ahead and look at some of the waveforms that we've seen in the simulation. So first of all, we can look at the outputs of the oscillators, quite large signals, and we can see the basic shape that we've seen in the simulation. So the bottom part is quite sine wavy, while the top part is cut off, so it's a bit flat. And our signal is one of the oscillators at least at around 320 kilohertz. If we look at the same thing on the other oscillator, we see a similar waveform, but at a slightly different frequency. So this one is at around 317 kilohertz, difference of the two being 3 kilohertz. So now if we look at the heterodyne signal, so the two signals combined, we see this thing. So these are the two signals overlapping. And now if I just bring in my cursors, we can see that the frequency of the envelope of this signal is roughly 2.6, close to 3 kilohertz. So we are getting the frequency difference between the two initial signals. Now, since the signal is so small, we can barely see it after detection. So this is where we should have the audio signal, but it's just barely visible. So you can almost make it out that there's a sine wave in there. And if we change the capacity on the antenna, then also this frequency changes. So if I bring my hand closer to it, the wavelength becomes longer. If I take it away, the wavelength becomes smaller. So I'm sorry, but because of all the noise, it's very difficult to make this thing out. So let's move on to the volume control side. Here again we see our high frequency signal. Again, same shape as before. The only difference is that this time it's a 700 kilohertz signal. Now this was intentional, so I have different components in the oscillators. And the reason for this is that when you're building a Theremin type of circuit, it's important that the volume control side and the pitch control side work at different frequencies. Otherwise, the heterodynamic phenomenon could appear between these oscillators, which should be isolated. So it's important that the difference or the sum or whatever mathematical operation between the two frequencies used doesn't end up in the audio spectrum. So finally, we can look at what comes out of the voltage controlled amplifier. Again, we see only noise, but when I bring my hand closer to the volume antenna, we can see that this noise is increasing. So even though it's not very obvious, the volume control is actually working. So it's by bringing my hand closer to it, I'm increasing the gain of the amplifier. Now, you may notice that this board has some components other than the ones shown in the simulation, namely these two things. So let's go to the final schematic and see exactly how this thing is built. and at the same time look at some other schematics, see how other people build this sort of circuit. So this is the final schematic that I've used, and from the simulation there are just a few differences. Namely, I've added series capacitors between the oscillators and the antennas, so that if you actually touch the antenna, you don't touch the oscillator. So you have this DC isolating element. I added filtration elements between the supply and the oscillator. So this circuit will work from 6 volts to 9 volts to, it doesn't really have a very specific supply range. So I added this filtering resistor and filtering capacitors. And finally I added this thing, so I have a potentiometer and a series resistance going into the base of the oscillator's transistor. Now I added one of these for the volume oscillator and another one for the pitch reference oscillator. The point of using this is that by varying the value of the potentiometer, you slightly vary the frequency of the oscillator. Basically, apart from the capacitors and the inductor used in the LC circuit, you also get a bit of a contribution from the transistor's capacity, which is dependent on the voltage in the base. And that's what you vary using this potentiometer. So these are the 3 oscillators, so you got the volume oscillator, the variable pitch oscillator, the one with the antenna, and the pitch reference oscillator. You combine the 2 pitch oscillators into the heterodyning signal, so you have this mixer and audio detector. And finally, you take the 2 signals and put them into the voltage controlled amplifier. And other than this, there's also a connector and a filtration capacitor on the supply. Now, if you don't like my schematic, don't worry, there's a lot of them out there. So I would just like to point out this website. It's called Theremin World. It has a bunch of information about theremins, and especially you have this section called Theremin Schematics, so don't worry, I'll leave a link to this in the description, where you have a bunch of schematics from all sorts of people about theremins, both vacuum tube, transistor, integrated circuits, you name it, it's probably here. And out of all of these, I would just like to point out this website. So this is a website owned by Mr. Arthur Harrison. So I highly recommend this website, go through the various articles, there's a lot of good information here. And basically that's all from my side. So I hope you like this circuit. If you want me to go into more details and make a better one, just let me know down in the comments. But other than that, hope you got some useful information out of this. Leave your thoughts in the comments, thank you for watching, make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.